Hi, welcome to the Olympiad geometry. Let's continue our study on the Simson line theorem. So here is the problem. PQ are points on radius OK of circumcircle of triangle ABC, and OP times OQ equals to OK squared. UVW are symmetrical points from P to line BC, CA, AB. QU, QV, QW intersect BC, CA, AB on point D, E, F respectively, shows that D, E, F are collinear. So when we get this problem, we can see that the point P has a symmetrical point W to the line AB, right? So we know that AP equals to AW, BP equals to BW, and we connect that QW intersect AB on point F. Similarly, we got point D, point E. We want to prove that FDE are collinear. The first question is that what can we learn from of the point P and point Q? The problem set is that OP times OQ equals to OK squared. OP times 2 OQ equals to OK squared. Right, that's a problem set. And we want to prove FDE are collinear. We can just recall we've been seeing this problem before, but at that time, both point P and point Q are on the circumcircle, right? Which actually meets a condition that OP times OQ equals to OK squared. It's just 2 points on the circumcircle instead of the 2 points on the radius. So we can, in that problem that we solved about 2 videos before, in that problem, we use the Menelaus theorem to solve that. And here we can still try to use Menelaus theorem, which means we have a triangle ABC here, and the FDE would be the intersection line. So we just need to prove that AF, right? AF to BF times AF to BF times BD to CD times CE to AE equals to 1. We just need to prove this. Right, we want to prove this equation is valid, and AF to BF, that can be rewritten as a area ratio of triangle AWQ, right? AF to BF, so AWQ to BWQ to the area of triangle BWQ times BD to DC, that's area of triangle BUQ to the area of triangle CUQ times CE to AE, that's area of triangle CVQ to the area of triangle AVQ equals to 1, right? These two equations are equivalent. So if we look at AWQ, it has a edge AW, right? AW, and another edge AQ, and another edge WQ. So anyway, it has a AW here, and another triangle that AVQ has an edge of AV here. So we know that AW can cancel the AV, right? Which means that we have, and WQ can cancel each other. So that means if we use AW and WQ, we need to figure out how to deal with the angle AWQ, right? And if we use, let's say this way, AV or AW and AQ, right, which we can also cancel AQ here, right? WQ can be cancelled here. So if we use AW and AQ, we need to figure out the angle relation of WAQ, right? So which edge to choose is kind of difficult to decide right now. Now let's come back to the condition that OP times OQ equals to OK squared. Let's see if we can figure out something from here and to tell us which angle to pick, right? OP times OQ equals to OK squared. OP times OQ equals to OK squared. It looks like very difficult to find any relationship from this equation or this problem set to the angle peak, right? Because all the angle peak are happen on the like angle AWQ or AQW or WAQ, right? So if we try on this, let's consider about point C. If we just connect OC, sorry, I connect OE here. Point C is this one. So let's connect OC here. It's very easy to make mistake. OC, and we connect QC. Also, we can connect PC, right? So we notice that OK equals to OC. That's the radius of the circumcircle. And we can translate OP times OQ to OC squared, which means we got OP to OC equals to OC to OQ, right? OP to OC equals to OC to OQ, and they're sharing the angle QOC, so we got triangle CQO is similar to triangle PCO, right? Triangle CQO is similar to triangle PCO. And based on this, we know that angle OQC equals to angle OCP. Would it be useful? We don't know. But just from this one, we can have, we already know this equation here, right? OP, OC, OQ. And let's think about OC here. It can be rewritten as OK, right? So we got OP to OK equals to OK to OQ as well, right? OP to OK equals to OK to OQ. So we can just do some derivation from here, right? OP to OK minus 1 would be equals to OK to OQ minus 1, which we got OP minus OK to OK, right? OP minus OK, OP minus OK, that's PK. PK to OK equals to, here, OK minus OQ, OK minus OQ, OK minus OQ to OQ. So that's KQ to OQ. Right, we got this, which means PK to KQ equals to OK to OQ. Right, we notice that OK to OQ equals to OC to OQ. Right, because OK and OC are radius, which means it equals to OP to OC. So PK to KQ equals to OP to OC. Right, and we know that OP to OC, OP is one edge of triangle OPC. OC is one edge of triangle OCQ, right? So OP to OC equals to PC to CQ, because that, so you can find it here. OP to OC equals to PC to CQ, right? So PC to CQ. Look at this. We got PK to KQ equals to PC to CQ. PK to KQ equals to PC to CQ, which means CK is the angle bisector of triangle of angle QCP, right? So we can connect CK. Whether it's useful, we don't know. We just try our best to find everything we can find, right? So now we have that. We know that CK is the angle bisector of angle QCP. Now we have an idea, right? Because it happens on this QCP, and we already know that P and V are symmetrical to AC, which means that angle PCA equals to angle VCA, right? Angle PCA equals to angle VCA. Right, because P and V are symmetrical to AC, so angle PCV equals to angle VCA. And because angle PCK equals to 2 twice of angle KCQ, right? PCQ, that's twice of KCQ. So we know that, look at here, this angle, the PCA equals to VCA, right? And PCQ is twice of KCQ. So if we want to find the angle of the angle of KCA, let's write it here. So angle PCV, let's write it as this way, PCV equals to twice of angle PCA. Right, so angle PCV minus angle PCQ. PCV minus PCQ, that's the angle QCV, right? And also equals to twice of angle PCA minus twice of angle PCK. Equals to twice of angle PCA minus angle PCK, which equals to twice of PCA minus PCK, that's KCA, right? Which we can get, look at here. So angle QCV is twice of angle KCA. Right. So QCV can be found here in the triangle CVQ, right? Angle QCV can be found here. So now we just need to find how we can relate this angle to another angle in all of these 6 triangles, right? Look at that QCV equals to twice of KCA. KCA is this angle, and if we just connect BK, we know that angle FBK, because ABKC are cyclic, so the angle FBK equals to angle ACK or KAC, right? So it equals to would be equals to twice of angle FBK, right? FBK. And now we can connect BQ and BP. Also OB here. Notice that OB equals to OC, so we can just change all the C here to be B, right? Because OB equals to OC, that make OC can be replaced to be OB here, and here can be OB here, right? So we can get PK2KQ equals to OB2OQ equals to OP2OB, right? And OP2OB. So we can also prove that triangle OBQ is similar to triangle OBP, just because OQ to OB equals to OB to OP, and they are sharing the angle BOQ, right? So means it equals to PB to BQ, right? So PK to KQ equals to PB to BQ, which means BK is angle bisector of angle PBQ. Right. So we got that BK is the angle bisector of angle PBQ. So we already know that PBF would equal to WBF, right? Because P and W are symmetrical to AB. So we got angle So let's write this way. So we want to find angle QBW, right? So, but we can start from here. So angle PBW equals to twice of angle PBF. So angle QBW equals to PBW plus QBP, right? Angle PBW plus angle PBQ equals to twice of angle PBF plus twice of angle PBK equals to twice of angle PBF plus angle PBK equals to twice of PBF plus PBK. That's an angle KBF or FBK. Right? So we find that angle QCV equals to angle QBW. Right? QCV equals to QBW. Again, QCV equals to QBW. Now we can look at this this side, right? The Menelaus theorem. We already know that angle QCV equals to angle QBW. Right, we know that angle QCV equals to angle QBW, which, because this is like symmetrical thing, so we can easily prove that angle, look at here, QCV equals to QBW, so QAW equals to angle QCU and angle QBU equals to angle QAV. Right, so this equation can be extended. So we want to prove this equation, right? So, but we can extend the production of this to be half of we want to find the QCW, right? So that's CQ CV. So here is half of AW AQ sine angle QAW divided by half of BW BQ sine angle QBW times half BU BQ sine angle QBU 2 half CU CQ sine angle QCU times here, so CV CQ sine angle QCV half AV AQ sine angle QAV, right? And we know that AW equals to AV, AQ equals to AQ, BU equals to CU, BQ equals to BQ. BU equal no, BU actually equals to BW. Sorry, not here. BU equals to BW, right? And CU equals to CV, CQ equals to CQ, and angle QAW equals to angle QCU. So QAW equals to angle QCU, QBU equals to QAV, QCV equals to QBW. So this equals to 1. The production equals to 1, which we can use the converse of Mendeley's theorem to prove that DEF are collinear, right? So let's just do a short review of this problem. At the very first, that we actually find the problem is a variant of previous problems that PQ are on the circumcircle of the triangle ABC, and it's just a variant that makes a PQ on the radius of OK. So we're thinking that we can use a similar way, which that we can use the Mendeley's theorem, translate it to the from the edge ratio to the area of the triangle ratio, and find the proper side of the triangle and proper angle ratio to cancel each other to prove the production would be 1. Right? The question would be which angle we need to find, and then we start from looking at this problem set to figure out the proper angles that we want to look at. So the thing that I want to say here is that this is a problem that roughly see on the IMO level, but if it occurs on the IMO, I would imagine that the problem just like this, right? There's no problem saying all PQ are on the circumcircle and then give you the variant. But we can think about this. So once the research do the research on a figure or on a certain figure, they derive the relation of the edge or angle step by step, right? And once they want to make it as a problem to you, they omit all the steps in front before the conclusion. So they just give you the conclusion, ask you to prove it. Basically, it's a way that to do the research. You can think it as a way to do the research. The research is that we can guess something first, and then we try to prove it. But how to prove it? We can first find some specific conditions to prove. And based on the specific condition, if we can prove that, right? Based on the specific condition provement, we can figure out a set of procedure to solve the problem, and we can borrow the idea of that solving the specific condition of the problem to make it to be a general solution. That's a way of doing research. So I hope you like this video. This, I think, is a very good example of how to do research by yourself, or how to learn stuff by yourself, or teach yourself. Yeah, again, I hope you like this video. We will talk more about the Olympiad geometry in the future videos. Thank you very much.